VLSos here. This is a video lesson on related rates. Related rates is a family of problems in calculus that use calculus to work real-world applications. And for students that are studying it for the first time, related rates problems can be quite challenging. So this lesson is an introduction to the concept of related rates, rates that are related mathematically. And then in future videos, we'll get into thorough examples of solving and completing related rates problems. Let's begin with something that is familiar to us. We can define a function, p of t, and think of this as a distance function. I use p instead of d because d is used in the notation for a derivative, so it would be confusing to use d as the distance function. So we're thinking of p as a distance function like a car traveling down a road. And we are familiar with the concept then, the derivative of p with respects to t, or the rate of change of the distance function, is velocity. And let's point out that velocity, even though it might be its own concept with its own equation, velocity at its heart is a rate. It's a rate of change. This is a familiar situation, a car traveling down a road. Its rate of change of its position is velocity. But let's introduce the idea that cars run on energy. It could be chemical energy in the form of gasoline or fuel. It could be electric energy in the form of stored energy in a battery, which also then might use a chemical process to produce the electricity. But regardless, we have a car that needs energy to run. And the use of the car's energy is dependent on its velocity. This ought to make intuitive sense. You need relatively little energy to accelerate the car to a low velocity. You'll need more energy to accelerate that car to a higher velocity. So there's a relationship between the energy use and the velocity of the car. We could think of then as there being another rate. And this rate will be expressed in the form of a derivative. The derivative of, let's say, g with respects to t is the gas consumption of the car. The rate at which the gasoline is being depleted to produce the energy that's necessary to change the position and therefore get a rate of change, which is velocity. We could sketch a graph that relates the velocity and gas consumption. And this is going to be a very crude and general graph. At no velocity, there's no gasoline consumption. Let's imagine that we're starting our car. And we consume a fair amount of fuel or energy in order to get the car rolling at a low velocity. But as the car increases the velocity, then we get more motivation out of the car for the relatively low gas consumption. In other words, I'm choosing this to not be a linear relationship. We get more velocity per gas consumption the faster we go, which generally models a car traveling on a flat surface down a road. The point in relating these is that the velocity and the gasoline consumption are related to each other. And the relationship would be the equation that then models or is this graph. And in this case, this is an example of related rates because velocity and gas consumption are themselves rates. Let's talk about related rates in another context. In this case, we're going to think of a teacup that is being filled with tea, pouring out of a teapot maybe. And the teacup has a shape that we'll draw. If we can imagine a handle attached to this teacup, maybe we can help visualize that we're talking about a cup. And we have tea being poured into the cup. And as the tea is poured into the cup, it pools at the bottom and creates a surface. In this situation, we can think of then a few related concepts. First of which is that the tea in the cup is a volume. And the volume is going to change according to time. Imagine that there is no tea in the cup. We start pouring, and then the cup fills up with tea, so the volume that we may be able to calculate if we knew the geometry of the cup would then be the volume depending on how long we were pouring tea into it. We could imagine that the rate of change of volume, dV over dt, could be anything, but we could choose it to be constant, a constant pour. No more, no less, a steady stream of tea going into the cup to create the volume. The volume of the cup, if we knew the geometry, could be calculated. And the calculation would be dependent on the height of the tea in the cup. What might help this computation is the radius of the circular surface of the tea as the cup fills up. We could label these measures height and radius. We could visualize that the height of the tea in the cup is going to increase as the tea is poured in. There is a relationship between the height of the tea in the cup and time. Over time, the height will increase as we pour. And so if there's a relationship between the height as a function of time, then we also have the rate of change of height with respect to time. We could think of this for the radius as well. The radius of the circular surface of the tea will increase as you pour tea into the cup. And you're pouring tea into the cup over time. But let's compare and focus on the relationship between height and volume. We have a graph that we're starting. And I could imagine the horizontal axis to be t. And we're going to graph two things. So the vertical axis is not going to be level because it's going to represent two graphs. One is the volume over time. And the volume is going to go up at a constant rate because the rate of change has been constant. Then the equation that models the volume will have a constant rate or be a line. Height, however, because of the geometry we can observe about this cup, will not be constant. The cup has little volume when the tea starts to pour in. And the height is going to go up very quickly at first. But as the cup fills and becomes wider, then it takes more volume or more time to fill up that higher, larger surface. So height is always going to increase, but the rate of change of height is going to go down. Height will increase quickly at first, always increase as long as tea is being poured in the cup, but the rate of increase is going to slow down. So it's modeled with a function like this. Looks similar to a radical or a root. In this presentation, we ought to be able to see that the height is always going to be dependent on the volume. At any particular time, you'll have a certain volume. If we're pouring tea in the rate of an ounce per minute, then after 2 minutes, we will reliably always have 2 ounces of T, which means that we will always reliably have a specific height. There is an equation that relates volume as a function of height, or height as a function of volume, because at every particular volume, we always have a certain height, and vice versa. If that's the case, then we can take the derivative of this equation and have within it the rates of change of height and the rates of change of volume. In this case, we can get to the concept of the rates being related by an equation, which would be the derivative of the equation that relates their values. What that equation is and how it would help us find the rate of change of height at a particular time would then be a complete solution process, which we'll offer later. Let's take a look at one more example of related rates. Imagine that we have a wall, and we're looking at this wall from a side view. We have a side perspective on a situation. There's a wall and a ladder that stands against the wall. The ladder is rigid and straight and a fixed length. The ladder meets the wall at a particular height we could call y, and the ladder is a particular distance away from the wall that we could call x. X is the distance of the base of the ladder to the wall. And y is the reach of the ladder on the wall. L is the length of the ladder. X and y are variables because we can change the position of the ladder. L is not a variable, it's a fixed length. The ladder isn't going to change its length if it moves. But let's think about movement. This is a dangerous situation if you're at the top of the ladder. If you move the ladder away from the wall, then your height on the ladder is going to go down. The top of the ladder is going to slide down the wall as the base of the ladder goes away from the wall or increases its distance to the wall. And in this situation, if the base of the ladder is slipping, then a person on the ladder is in a dangerous situation. But we can think of change and the rate of change. dx over dt, if it is greater than 0, means that the base is moving away from the wall. We can visualize the position of this point moving to the right. X is increasing, so the rate of change must be positive to increase that value. And if X is increasing, then Y is going to be less than 0. The reach is going to slip down. So the top is sliding down. These rates are related. If we change x, y will change as well. But how? How do these rates relate? We know that if we're going to talk about how the rates relate, we need to relate the variables themselves. The equation that relates these two variables is the Pythagorean theorem if the wall meets the ground perpendicularly. X squared plus y squared is equal to this fixed ladder length squared, the geometry that relates the variables. And if we want to relate the rates, we take the derivative of this equation. We would do so implicitly, And if that's the case, if we do that, we get 2x, and then we're going to treat x as a function of time. So we must multiply, as if we're using the chain rule, by the derivative of x with respect to time. The derivative of y squared is 2y. Treating y as a function of time, we chain rule the derivative of y with respect to time. And L is a constant, so its derivative is 0. We have then an equation that relates the rates that we've identified. And if we had values for any of these four values, x, y, dx, and dy, then we could use 3 of those values to find the fourth and complete a calculation. One more thing to say about this situation is that many people might think that the rates or the ways that these variables relate is that when you increase x, then you will decrease y by the same amount. If you decrease x, intuitively you might think that you increase y by the same amount. But that's not the case. You can do a little experiment yourself and imagine that you have a ladder that's right up against the wall. So you have one endpoint being the height and one endpoint being the base. And if you move the base a full inch away and observe what happens to the top of your pencil, it's not going to move down by an inch. So the rates of change of these two related variables in this situation is not direct. The Pythagorean theorem that relates them is not a linear relationship. So it'll be a little more sophisticated than some might first think, as these often are.